All right, question 2 is the confirmation question, and unfortunately some of you got off to the wrong start with it by drawing the wrong structure. So it's very important when we're going to do a confirmation structure that we actually start with the correct chemical structure to begin with. Otherwise the Newman projections are meaningless. So begin there. Propane, 3 carbons, 1,1 dibromo, 1, 1, and then a 2 dibromo. So for the place where we're going to have a problem, there's going to be interactions between the substituents on this carbon and this one. On the far right, we just have methyl groups, just have hydrogens as our substituents, so they're not going to be a problem for us. It's the bromines interacting with each other, or a methyl group interacting with the bromines is going to be our problem. So this is our bond of interest between carbon 1 and carbon 2. So whenever you're doing this, you just basically need to take one of the 2 carbons and lock it down. Doesn't matter which one, your answers will be exactly the same. Just make sure one of them doesn't move so that you don't get confused and duplicate one of your Newman projections. So I'm going to take this as my front carbon, the one with the 2 bromines, and I'll leave this one as the rear carbon. And I'm going to fix that one. I'm just going to leave that one where it is and not touch it. So I'm going to start off with, since I'm drawing Newman projection, a confirmation, I'm going to have 6 of them. They may be energetically equivalent, but there's going to be 6. Because we're talking about 60-degree increments going from eclipse to staggered. So there'll always be 6 to look at if we're dealing with an open confirmation. That's different if I'm looking at ring structures. We'll talk about that with the cyclohexane questions. So in the back carbon that I had labeled before, I have a hydrogen, I have a bromine, and I have the 3rd carbon of the chain, so that's going to be a methyl group. So since I'm not messing with that, I'm going to put that back in place for all of these. That way I don't get confused and draw it wrong or rotate it accidentally. I strongly recommend you do this. And I said that before the exam, that you just need to freeze one of them, don't touch it. And that's what I'm drawing here, that we get those locked down. And out of the way. So then we can talk about the other carbon. The front carbon has 2 bromines and a hydrogen. So for starting off, we'll just begin with one of the staggered conformations. It does not matter which one. We're going to get the same 6 ones when we're over anyway. So I'm going to just go ahead and Roman numeral these so I can talk about them when we're done. You could use letters if you wanted. I try not to use normal numbering system here just because I don't want to confuse it with the naming system that has, 112 written on it. So I use either Roman numerals or I use letters just so that I can identify which structure I'm talking about. So each one of these is going to move 60 degrees. So I'm going to move from staggered to eclipsed to staggered to eclipsed. It doesn't really matter that what order I draw this in or which way I rotate them. I'm just going to rotate the front one clockwise. It's easier for me to see it that way. I'm offsetting it slightly because drawing a true eclipse is just messy. And then keep drawing around from there. Now, one thing that I think was less clear than people had hoped it would be is that eclipse confirmations are always bad. This is a much higher energy than any staggered confirmation. So we're always going to have a problem when we have eclipsing interactions, even if it's just eclipsing interactions with hydrogens. Because that is still getting awfully close to each other. And you can even see that with the ethane conformations that your book shows, that it's not a great energy jump, but it is a jump to have the have even hydrogens eclipsing each other in conformations. So in terms of what's the most stable here, the eclipsing ones are never going to be it. Big interaction problems are when we have something other than hydrogens. So I've got a big eclipsing problem here, and relatively big ones here, with large bromine having to go past the hydrogen that's existing there. That's going to be the case for all of these. Basically, eclipsing interactions, everything is a problem except for possibly those two hydrogens. And again, it's not large interaction, but it's not zero either. So there is still a problem there. It's just not defining in terms of most structures. So those are all eclipsing interactions that are unfavorable. So those are all going to be very much higher in energy than what we're going to deal with in any staggered conformation. So those are out in terms of being the stable one. So then with the staggered conformations, what I've labeled here is 1, 3, and 5. We're looking at groups that are not hydrogen that are gauche to each other, 60 degrees apart. So I have that relationship here, I have it here, and I have it here. So I've got a continuous set of 3 different gauche interactions for conformation 1. I have the same problem with conformation 3, that these are all gauche butane interactions, but they'll be larger than that because the bromine is larger energetically, more of an energetic problem than methyl groups getting close to each other. The repulsive force is going to be more significant there. So I have 3 different gauche interactions for both structure 1 and structure 3, or projection 1 and projection 3 here. Whereas here, for projection number 5, I only have 2 of them. The rotation has now gotten that continuous set apart from each other. And as a result, it's taken down the number of interactions that are problematic by 1. So in terms of which of these structures has the least problematic arrangement of the groups, it is structure 5. This is my most stable one. Least stable is going to be where I have bromines on top of each other and a bromine with the methyls. So least stable is going to be either 2 or 4, but I didn't ask that. But this is a massive interaction. Is going to be 2. Where I have now 2 bromines interacting and a bromine and a methyl. That is much worse than the bromine-hydrogen interactions that you see in structures 4 and 6. So this is the worst energetically, structure 2, and projection number 5 is the best energetically because I have a minimum number of gauche butane interactions. It's important to remember that in some cases that's not going to get down to 0 like this one. In something like butane, I can rotate the 2 methyl groups anti to each other. I have no negative interactions at that point. That's a very simple structure. And once you add 1 more atom to that structure, you're not getting a 0 interactions conformation anymore. So then it's a matter of the lesser of 6 evils. Which of them is not as bad as the others? We're going to come back to this, and we already have, in terms of structural requirements for the SN2 and E2 reactions, specifically the E2 reaction, because we may have to go to a conformation that's less favorable to get that reaction to work. So this will come back to haunt us time and time again, which is why it's covered earlier than a lot of other reaction topics in your textbook.